is about how we can use the information that impedance is calculated in a statistical way. So here there are some slides with some equations only, but nothing special, nothing that heavy like yesterday. I will not go into the equations. I will just explain what do they mean in the background and in the practice side of it. So what are we going to cover today? These are 4 simple topics. The focus will be mainly on how to exploit the fact that we have statistical properties of the impedance. So I'm going to talk about automatic change detection in ice curves. I'm going to talk about how to analyze DRT curves automatically. And I'm going to show you today why we can get out analyzing DRT curves without any issues for regularization. It will be based on the concept of optimal transfer. So these are these tools that I'm going to present are quite common in the field of analysis of stochastic data, predominantly probability distributions. It is somewhat new to the field of electrochemistry, but I'm going to present actual results from actual experiments that will show the effectiveness of these approaches. And as last 2 days, I'm going to give you the complete numerical implementations for everything that you will see here. So first thing is, let's discuss the issues or the benefits of having statistical input signal and output signal. So as I was told yesterday, I will not write in this right corner because it's not visible. Sorry about that. So what is the status that we are currently at? So yesterday I was describing that we have stochastic signal at the input plus some noise. Then we have our electrochemical system that we say that it's an ideal one. But because there are a lot of processes going inside, we can, on the macroscopic level, see that this parameter might be stochastic. This doesn't mean that the values of, I don't know, capacitors or resistors change dramatically. They are quite narrow. So it means that the values are really close, but we can allow for their values to vary just a little. So, and then at the output, we have our measurement noise and output signal. And this output signal is then also stochastic. So we have stochastic input and stochastic output. And based on these blue circles, we are calculating our impedance. What does this mean? It means that even if we measure impedance at several really close time points, we will never expect to get the same point over and over again, but the values for particular frequency will just flicker around. And how this spread, how big is this spread, will depend on the properties of the input signal, the properties of the output signal, and most importantly, the properties of the system. So today, I'm going to show you that it's not a problem to have such a stochastic concept, but it is actually a beneficial, and we can use these uncertainties in our own advantage. So first things first is, can we somehow describe the probability distribution of our input signal? I'm not going to go into any details of deriving any equation or any of this. You can find these papers here where this is described. What I want to, what is important, what I want to tell you is that when we calculate, when we have stochastic signal like this, which is really close to white noise. So in theoretical context, if we have white noise, then when we calculate its spectrum, we will have real and imaginary components. And the real component is distributed by Gaussian distribution with zero mean and some variance. And the imaginary component is also zero mean and some variance. But the beauty of it is, if we draw now the complex distribution of these two things, we will get a distribution that has concentric circles positioned and at their corresponding mean values, in our case 0, and the real and imaginary component are not correlated. So I said a lot of things. What is most important thing that you have to remember is something that is called complex circular random variable. This means that the distribution functions are concentric circles. And it means that if I rotate it, I don't change the shape of the distribution, because if the distribution was like an oval, when I rotate it, it won't be the same. But if they're concentric circles, it doesn't matter how I rotate it, it looks exactly the same. So this is just, if you want to go deep into this, you have these papers here. The only thing that you have to just remember is that the distribution of this white noise are concentric circles. That's the only thing. And in order for this thing to be concentric circles, it means that the shape is dependent only on the modulus of this complex variable. But let's forget this for a time being. So why is this important? Well, we are putting a noise through a linear, and this is the really important part, through a linear state. So if we have, so if we go back to stochastic variables, if we have a stochastic variable, let's say x, and we pass it through, and we defined a new random variable y as some function of x, the question is, what is the distribution of this y if we know the distribution of x? Well, if this y f of x is linear, which in our case is, because we have a linear system, it means that under some circumstances, under some cases of the original distribution, the output distribution will belong to the same family. What does this mean is, the focus on this figure here. Assume that we have some shape, and this is our input distribution, and we do some linear transformation. So we scale it, we move it around, rotate it, whatever we want, those kind of linear transformations, also called in mathematics affine transformations. This means that the shape of these leaves is preserved. We don't distort the shape of the leaves, and consequently, we do not distort the shape of the probability distribution. And this is important, and it's not a case with any type of distribution, but if we have complex Gaussian, as we have here, complex Gaussian distribution is is called to be closed under such linear transformation. So what does this mean? It means that the output signal here, everything what I was just talking gibberishly maybe for you, this is the important part, the output distribution will have the same shape. It doesn't mean that it will be identical, but it will be the same shape, maybe a little squashed, maybe expanded, maybe rotated, but visually it will be in the same family as the input signal. What does this mean in essence? This means the following. We have, in our case, when we do ice, we have a distribution of the current and the distribution of the voltage. Both belong to the same family. So their real and imaginary components are Gaussian, each with their own variance. So this is change. The diameter of these circles can be contracted or expanded, but the shape is the same. So if we remove the numbers on the graph, you will not be able to distinguish which distribution I'm talking about. They will look the same. If we put the numbers, you will see that one is bigger, the other one is smaller or whatever, but they will have generally the same shape. This means that they belong to the same family. Why is this important? Well, we can now derive the distribution of our impedance. What we have, our impedance is voltage divided by current. I told you yesterday that we never do this division. That is true. I'm going to show you now why we are not doing it. And we know that this is distributed as complex Gaussian 1. And now, because we are talking about linear system, this is distributed by complex Gaussian 2. They have their own parameters. Nobody cares at the moment. We will come to the parameter estimation. And we want to divide them. So we have a random variable now, Z, which is our impedance. That is U divided over I. And our question is, what is this Z distributed according? And what is derived here, I'm not going into details, is something that in statistics is called change of variables. Change of variables. You can, it's a typical example. So we are looking at a joint distribution, find its Jacobian, do some transformations, and make some integration. You can find it on Wikipedia or whatever. I'm not going into details because this is really basic stuff in stochastic analysis. If you don't know it, doesn't matter. That's why I'm not dwelling into it. The main thing that I would like to tell you is that we are having an input signal and an output. It doesn't matter whether it's a current or voltage. I chose something randomly. But these signals, because they pass through a linear system, they are correlated. And this correlation, how each frequency of the input is correlated to the output, is actually the impedance. And because these two are correlated, and these two are circular Gaussian 1, circular Gaussian 2, we can say that their joint distribution has a covariance function like this. I will come to these parameters. And if I plug this here and solve these integrals, luckily they can be solved as in symbolic way. This equation pops up. So I'm not doing any division at the moment. And this is the distribution of each component of our impedance. It doesn't matter how it looks like. The only thing that you should take notice are the following three things. it depends on the variance of the input and the output plus the correlation coefficient, which we will show now that it is the true impedance. How can we show this? Well, we take this, let's first forget about this part at the moment. I'm not going to scribble around it because I cannot divide. Let's draw this function because it is a complex one. It has real and imaginary component. We are going to draw it here. So we have real and imaginary. And this function was drawn by assuming that we have 4 units of variance in the input noise and 1 unit of variance of the output, whatever that means, volts, amps, doesn't matter. And we are saying that input and output are correlated by these values, 1/4 plus J 1/4. And if we draw it, we see those concentric circles here. And the mean value is here. And the mean value is our measured impedance at that particular frequency. So we have circles like this for each frequency. So in order to find the impedance at one particular frequency, we have to find the mean value of this function. And if we calculate it, although the integral seems really, really complicated, it reduces down to this value. So the impedance is dependent only on the variance of the input, the variance of the output, and the correlation coefficient. So we have to somehow, from our signals, estimate only these parameters, and the impedance will pop up. And this is a consistent, unbiased estimation. This means, like a mouthful, a lot of mathematics. And how do we come up with it? Well, it is rather simple. So we want to calculate this. We said that input and output are normal like this. And now I'm going to show you how we can estimate these parameters. Let me see if I have this plotted. Yes. So what is the case? So now we are actually coming to this part, which was a little bit convoluted yesterday. So we have a noise at the input. And I draw it like this because I don't know whether we are exciting with current or with voltage. It doesn't matter. What I showed now is that this is complex Gaussian 1 and this is complex Gaussian 2, which means that they belong to the same family. They're not identical, but belong to the same family. And we calculate this wavelet transform yesterday from the input noise and from the output noise. And we get this chaotic complex maps. And everything what we have to do is using these values here to estimate these parameters. How can we do it? Well, let's see what we have. We have to find a variance of, let's say that the voltage is our input. Voltage is input, right? In our case, it can be the other ways around. So we need to calculate the variance of the input at a certain particular frequency, or all of them. This is the wavelet transform of the input. And we select one frequency at which we want to calculate the variance. And if we select this frequency, we will get the signal how it was at that particular frequency. It will be noise. And we say, what is the variance of this at this frequency? And we're going to get this thing. We're going to repeat exactly the same thing for the output. At the same particular frequency, there will be a different shape of the noise. We will take the variance. I mean, if you type MATLAB or whatever, it is just a command, var of some vector. And it is in essence this sum of x, y minus mean of xy squared. That is it. This is the equation. Nothing special. And we get this value. And then the last thing what we need to do is calculate this thing. How do we calculate it? So it is sum of current minus mean of the current times voltage minus mean of the voltage squared. And we are getting this. Everything comes from these two maps. This map is y, this map is u, and I'm calculating this. Sorry, stop Siri. And calculating this and this using these two maps. So I now have all these values, and I'm interested in rho. And I can easily calculate it now because I have three equations with three unknowns. These values I got. And I can just swap it, and I'm getting the equation, the result for my impedance flat out. That is how it is done. So what does this actually find? This looks like a nice numerical exercise. It is numerically stable. Everything is logical. But what does this help me? I mean, does it have any practical meaning? Well, actually, what we can do now is the following thing. This part around is the thing that I was explaining now, and you can just forget it at the moment. Just say that, okay, we know these distributions. Let's say that we can understand what it is, or maybe not. The practical implications are the following. Let's say that we have an experiment that has that tracks evolution of ice curves over time. And we have a reference ice curve here, and maybe a target after some time ice curve here. And if we look at these ice curves, we can say, yes, there is a clear difference between the blue one and the red one. I can see it, so I don't have to do anything. There is a clear difference. But the question is, can we do this automatically? Can we have an automatic system that can consistently detect these changes and quantify them without any human intervention? Well, since we now have the distribution functions of each frequency, just imagine that such clusters exist at every point here. So I'm not to overload the image. I just plot it for one frequency. There is a cluster in the source distribution and cluster in the target distribution, and in the target ice. And since I know these red and blue distributions, my problem now changes not from looking at ice curves into actually comparing to probability distributions. In mathematics, we have a million tools for comparison of two probability distributions. It doesn't care where the probability distributions came from. If I have them, we have tools how to compare them. And today, I'm going to show you two particular cases how we can exploit this concept that we have distribution of the impedance in order to do automatic analysis of ice curves. And we are going to do it through checking how the distributions of particular frequencies are changing over time. One can say, firstly, okay, fine, I can check the variance of the distribution. Well, there is one major problem here. If we take this distribution, which is complex, and check how its real and imaginary components look like by simple integration, luckily, this can be done in a symbolic way. We are getting this relation here. Again, it's a huge one. Don't worry about it. This is the most important part. It says power to the 3/2. This means that if I try to find the variance of this distribution, which would be integral of x minus it will be, let's say, imaginary z minus my squared time this f of x from minus infinity to plus infinity. This integral does not converge. It means that these distributions do not have a variance. I mean, we cannot calculate its variance. Although it's not visible here, statistically speaking, they have heavy tails. This means that there is a sufficiently high probability that the impedance can jump really high left and right. And someone will say, okay, this never happens. Correct? Yes. But our statistical tools are saying that we cannot calculate variance. These distributions belong to a family that is called stable Levi distributions, and they're rather complicated. And for fun of it, practically everything what we have in Mother Nature converges down to such distributions. So we have no variance, so we cannot calculate some fixed intervals. It's rather difficult. What we can do is we can use an approach in statistics that is called sample testing. I may be bombarding you with a lot of unknown terms, but now we are coming to a practical results where everything will be just converging to something, a really, really clear picture. So what we would like to do, so we have impedance at time 0 and impedance at time 1 or time n. And we would like to compare these two impedances. We know the PDF at time 0, and we now know the PDF at time n. We know that these PDFs are problematic, but we have their samples because we measure them. So how can we compare and say whether these two samples, the question is, the two impedances are the same if the observed samples came from the same distribution. So how can we reliably detect that the two samples are coming from the same distribution? There is something that is called Kolmogorov-Smirnov test. And this test asks a null hypothesis. Are the observed samples having the same distribution as the nominal samples? In our case, does the components of the ice now have the same distribution as the components of the nominal case of ice? This means that ice curves did not change over time. How this test works is actually they draw, you take a cumulative distribution function, so you do a cumulative sum of your samples, and you have graph like this, and the test tries to find what is the maximum positive and maximum negative frequencies, maximum negative distances between these samples. And the beauty of the test is the following. This is the most bizarre scenario. It doesn't matter what is the actual distribution of these red and blue dots. The differences always follow this case. And this is Kolmogorov's distribution. So now we have two samples, and we can check whether they're statistically the same or not. How is this working? This is working in the following case. Let me draw this. I think that we have. So, and I'll come back to the test. So we have our original distribution and our target one. And we would like to put a threshold somewhere and say, if the differences are above this threshold, then we can say that there was a change in the ice curves. If it's below this threshold, there are no changes in the ice. Usually, we put this threshold at 99.5% or maybe 95% or whatever. And by putting these values, we can determine whether we have reliable change in the ice curve or not. There are two things that we have to consider when doing this analysis. And you were going to see that I'm not talking about ice anymore, but I'm talking about hypothesis testing. It has nothing to do with ice system, because the only analysis that we did from the last 3 days is to find these distributions. So there are two things. If you have no practical experience with this hypothesis testing, I'm just going to give some basic concepts. There are two things that we would like to consider. It's so-called type 1 error and type 2 errors. Type 1 error is saying that we are thinking that the sample is above the threshold, but it is actually the true value is not. And the second case scenario is we think that the sample is the same, but it is actually not. So these are so-called type 1 and type 2 errors. How can we make the type 1 error 0, so we don't want to make mistake, if we put the threshold to infinity? We say that if our observed value is infinitely away from us, then it is most probably different. That is impractical because we will never trigger the test. So when we say we are doing 95% accuracy, it means in 5% of the cases, we will have an impedance values higher, but they are higher just by chance. Nothing changed in the impedance. We are having this 5% error just by chance. Imagine that if I go to a population of people and start measuring blood pressure, we are saying that nominal blood pressure is 120/80, but it's not a fixed value. Each and every one of us has a little different blood pressure with some differences. And we can come up with an individual that has nominally higher blood pressure, but he doesn't have hypertension. His body is working like that normally. We don't have to medicate that person, but we're going to make a type 1 error. We're going to say, oh, you have hypertension, but actually he doesn't. He's just by chance above the threshold. That is the same thing here. So the only thing what we have to decide is what is our acceptable threshold level. Can we survive with 5% error, or maybe 0.5% error, or whatever? And that is our own choice. That is a design parameter. There are no guidelines. If you start to ask me what is the proper one, it is something that is acceptable for you in your case. Can I survive with such and such percentage of wrong testing? So, how do we apply it to impedance data? So all we have to do is find the threshold, determine or select the threshold that we are happy with, and just call something that is called Kolmogorov-Smirnov test. You don't have to calculate anything. In every possible numerical library for statistics, there is a function that is called Kolmogorov-Smirnov test, and that function does the following calculation. You don't even have to think about it. It is implemented there, and it will give you a p-value. And if the p-value is above this, then it will say, I can reject the null hypothesis. It means that the sample that we are looking doesn't come from the same distribution. If it is below this test, it says I cannot reject the null hypothesis. It doesn't mean that it comes from a different distribution. I just cannot reject it. It's not exclusive. Let's see actual results, how we can calculate this. Well, the process in Python is rather simple. Up until here is everything what we have done already. So we have wavelet results from the current and wavelet results from the voltage. We have, this is not anymore element division as we saw. We have the distribution of the impedance components. And for each and every component, we are having samples that we measure from our this wavelet transform. We have samples for this frequency, samples from the other, and so on and so on. And these are our samples. We have subsamples from the current distribution and exactly the same samples at exactly the same frequencies, from our nominal distribution. And we would like to compare these pairs of lines. Are these lines identical? And this is where we do Kolmogorov-Smirnov test. Let's see the actual results. So what I have here is a simple equivalent circuit model. I'm going to go through actual experimental results. What I have here is a simple RQ model, and I'm going to change the values of this pole by 5%. And I'm drawing the modulus of the impedance here. So this is when I change R2 by 5%, Q2 by 5%, and alpha 2 by 5%. And we can immediately see here, this is the blue one is the reference. The blue curve is the reference one. We can see if we zoom here that there are changes in this region. For Q, the changes are not clearly visible. And I'm doing noiseless simulation. And when we do alpha, we see that the changes are in this region. But if I take these values and plug them through a Kolmogorov-Smirnov test, this is what I'm getting. So we are saying that these are the intervals where I can safely say that these are the frequencies where I can safely say that the impedance changed, which is right here where the changes are visible. For Q values, the changes are in the high frequency part, here somewhere. We don't see it, but the test says that they're statistically significant. And they're in the same area for alpha. Here, this is where we can also visually see it. But we don't have to look at it with a magnifying glass and scratch our heads. Is this significantly enough to call it as a change or not? We can just leave the Kolmogorov-Smirnov test to do the job for us. This gives us the frequency intervals where we have statistically significant changes in our eye space without any human intervention. The only thing what we had to decide is how sensitive we would like to have our test. So these are the actual p-values that I was plotting here, and these are the intervals where we can reject the null hypothesis and the intervals where we cannot reject the null hypothesis. So it says here that here we can reject it. There are changes. Here we can change. There are changes, and here there are changes. Sadly, I was drawing. I now saw that the x-axis are not in the same span. Sorry for this. I will change it. So let's do it for. There is one really problematic part when we do this hypothesis testing, not just with Kolmogorov-Smirnov test, but in general. The problem is that we have this null hypothesis which says the impedance did not change. And we can say that it is true, or that we are out somewhere, but we don't know where. Does it mean that it's changed? What is the inverse mean? And because we don't know the inverse, it is called alternate hypothesis, and we can have infinite alternate hypothesis. It didn't change. It blew up. It shifted. It whatever happened. And because we don't know the alternate hypothesis, we have to somehow determine so-called power of the test. So what is the probability of being somewhere else? In order to do this, there are no formal tools how to solve this issue, but we can do it numerically, and we can do it for your own example. You take one impedance and generate random samples of it because you already have the distribution, and start adding some error, manually add some error, and see at which point your test will start to fail. I said a lot, maybe not clear enough. Let's show it on an example. So what I did here is I took an impedance at a particular frequency. Let's say that I have this for the input, and I have this for the output signal, calculated already, and I selected one frequency range randomly, here and here. And I want to see how much should I change, how much change should be imposed on this value to say that something happens. The only thing what I can select here are two things: the threshold value and how many samples do I need. How long should I measure my impedance? And these are the results. Alpha 0.001 means that I would like to be 99.999% certain that I am making proper decision. And as you can see from the first figure, if I have small amount of samples, I make a mistake. My test is rather sensitive. Even small changes trigger it. But if I take more and more samples, my tests become really precise. I can be certain that I will be capable of detecting even 2% of changes in the impedance. Here, if I have small number of samples, I can be certain when there is plus minus 10% change in the value. If I take more samples, my accuracy becomes extremely powerful. So I can actually increase these values quite a lot without making a lot of errors. And these 1,000 samples is not even that problematic for us because we make long measurements. This means that we can be really certain at what we are doing in such a test. So let's see real results. What I'm going to show you now is a water management fault of a PEM fuel cell. So we have a PEM fuel cell that was running nominally for some time. Then it went through a drying phase. Then it went through a flooding phase. And then we put it back to a nominal phase, whatever that means. Actually, we return the humidity of the PEM membrane to its initial condition. And these are the results of the Kolmogorov-Smirnov test. And I'm going to go deeper now to explain each and every point. And I'm going to show you the ice curves also. The first, so these lines here show the analysis of each and every ice curve. The first one, this column here, is a reference one. We've selected ad hoc that the first one is fault-free. And if we compare first one with itself, it says, yes, I'm the same. There are no errors anywhere. The green line, the green color says that there are no errors. Then we start operating the fuel cell and introduce flooding here. And I will come back to this part and discuss it. Then we remove the flooding here. Made one measurement and started. This was drying, sorry. This was drying, and this was flooding. We start flooding here up until this point. And then it was going back to normal. What we can see on this figure is the following. When we started, everything was okay. This column is completely green. But then, as we immediately went over, our test said that there are some changes in the frequencies above 100 Hertz. And this was consistent constantly. In this part here, everything remained okay. Then when we start flooding it, it says there is a change in the ice curve everywhere. Then we have one measurement in between, something returned to more or less normalish, except for high frequency bands. Then when we did drying, it says the ice curves changed everywhere. And then we did 4 more ice measurements after the flooding, but we never managed to recuperate the ice back to the original. So you're going to say, fine, okay, this might seem logical, but can we see the ice curves so that we can double check that this happens really? Okay, so these are the ice curves. How should we read the graphs? And I'm going to go in detail into each and every one of it so that you can get an idea. So the reference one is the blue ice curve, and it is always number 1. It is this one. This one is number 1. This ice is number 2, and so on and so on. The last one is number 13. Yes, I think. So let's see. It says a comparison here between ice number at measurement point 1 and ice with measurement point 3. Let's see the results first, and then I'm going to jump back and forth here. So ice, let's do it like this. I'm going to stop my presentation just to clear this. Right? I do it one more time, it comes back. I'm going to stop my presentation, start it one more time just to clear the screen. So all my jibber jabber is gone, so that I can scribble one more time. So let's see what was changed in impedance number 3. 1, 1, 2, 3. So these are the changes. It says that there are some changes just above 1 Hertz, some changes around 5, 6 Hertz or 4, and some changes above 100 Hertz. These are the changes that occurred. So why wasn't this nominal? It should have been green all the time. Well, we did the experiments partially improperly, and then on purpose we left it like that. When we start the PEM fuel cell, we didn't wait for a running time. And we said that the first ice, what we did was a proper one, but it needed some time to humidify itself and so on. So the actual first nominal ice was not a proper one. But anyway, we left it because it shows how sensitive the thing is. So let's see in detail the ice curves what we have. It is clear that around 2 Hertz we have changes. There are some small changes here around 9 Hertz, but everything above, this is a zoom value of this period, of this interval here. In the higher frequency range, both ice curves are one on top of each other. There are no visual discrepancies. But if I go back, we can see that we detected some change here. Where did it come from? What we are plotting here is the mean value of the impedance. So if I zoom in here, we have something like this. And hold on, sorry. Okay. So if I zoom in this area and try to draw a PDF of a particular frequency, let's say this 88 Hertz or this 500 Hertz or whatever, we will have something like this. The nominal would be really narrow, and the target would be also really narrow like this. And they're one on top of each other. But because their variance is so narrow, because we are so precise in those measurements, even small changes are statistically significant. And we can say safely, that these are intervals where we have change, statistically significant, and these are. Everything else is constant. We don't have to look at the ice curves anymore. Let's go to the next one. So we have 1 and 7. And let's see where we can say that there are changes here. We say, okay, in the low frequency part, somewhere around 10 Hertz and below. And we can see changes here in the high frequency part from 60 Hertz onwards. We can see it visually. Everything else for us visually seems more or less on top of each other. Let's go back to the Kolmogorov-Smirnov plot and see what is it telling us. So this is number 1, number 2, number 3, 4, 5, 6, and this is number 7. And we can clearly see that this part is not included in this statistic. We don't have to look at the ice curves anymore. It just pops up. And yes, then our expertise comes. I'm not saying what is the cause of changes in those high frequency ranges, but I'm just saying that there are changes there. You don't have to look at the ice curves anymore. Let's go next. The next one is 1 and 10. 1 and 10 is clear. The low frequency part is clearly different, and we can see also at the high frequency part discrepancies. These changes are really big. These changes are rather small. These changes are rather small, but let's go back. 1 and 10. So this is 10. It says changes almost everywhere. All of them are statistically significant, and so on and so on. The one here, 1 and 20, is everywhere. You can see it. It's crystal clear that the impedance changed, but we don't have to look at it. We can just take the Kolmogorov-Smirnov. That's the beauty. There is an additional variation of this change, of this test. It is called lower and higher. So if I go back to this slide here, just to give you an idea. Come on. So we were looking currently at this plus this. We were looking at the so-called two-sided test. But we can look at something that is called only one-sided test. How much did something increase, or how much did something decrease? Separate. We don't want to see how general change happened, but we would like only to concentrate on the increases or on the decreases. We can do this, and it's called one-sided test. It's built in every library. And these are, on the exactly same experiments, one-sided tests. Now the maps, this one on the top, are rather different. So what we can see here is that now the test is sensitive only to intervals. So this is, I think, on the small side, where we have changes below, and this is where we have changes above. So let's see this part. So this is 1 and 10. No, this one is better. So look, 1 and 20. So we can see that at the low frequency part, we have the new one, the orange one is above the reference one. So this is where it failed, but it is not below. Everything else is okay here, because this one looks only at increase. But if we go to the smaller side, we will say that on the same impedance curve, we have changes on the higher frequency part. So the low frequency part is higher impedance than the nominal one, and the low frequency part has the higher impedance, and the high frequency part has a lower impedance. Even we can track this without looking at the I-square. We can see those changes where it goes up or down. The previous test was looking just at changes. Doesn't matter what kind of changes are there. Now we can look whether the change in a positive way or in a negative way is significant. And this is called one-sided test. Now we can go even further in the analysis of our I-squares. And the second concept is called divergence. So what divergence measures in impedance, in probability distributions, actually try to calculate what is the, now in huge quotation mark, what is the distance between two probability distributions. There are a lot of definitions how this divergence operate. I'm not going into details. The goal is for you just to realize that there is such a tool that can measure how distant are two divergences. Let's see how can we exploit this. So there are a lot of variations. I'm not going into any details. Numerically is everything implemented. Most probably you've heard of something that is called Kullback-Leibler divergence or Renyi divergence. Those are the equations. Let's forget about them at the moment. I discuss it when we come back. Experimental results, just to see how everything works. We have a solid oxide field cell. We measure temperatures at these points here, and we have three operating conditions that are presented here in the table below. So current densities were changing, fuel flow, the ratio of hydrogen and water, and the temperature was changing. So these are the table. This is the table of the changes, and we would like to see how the impedance evolved over time. So for each of these conditions, we measured around 60 impedance curves. So on the top plot, we see the voltage. This is the first one. This graph is voltage. These graphs are temperature changes, temperature changes, and this is the current relative temperature change, and this is the current. The relative temperature change is in percentage points based on the initial measurement at that point. And we are measuring temperature in these points on the fuel cell. So the spikes that you see here on the voltage are the same, are the places where we did ice curves. As you saw yesterday in our experiment, when we start ice, you can see it on your voltage monitor that there is some jitter. These are the spikes, nothing particular. These are the points where we're doing excitation. And on the lower left part of the screen, you can see the 60 ice curves. The red one is a reference. So the red one is the very first ice curve, and the blue one is the very last one. Shades of gray show the time evolution. So we started from a red ice curve, and slowly the system evolved towards the blue one. The question was, what was happening in the system? Can we say when did the change occur and in which frequency interval? Yes, we can start looking at those ice curves by hand, try to determine it, or we can use the fact that we have distribution for each of these points and just use some for sort of divergence. And these are the results for the divergence cases. So what we did is we took that this is a reference distribution, and each of these next points are target distributions, Q1, Q2, all the way to Q6. And then we calculate the difference for each frequency between the starting distribution and our target distribution of the impedance. And what we have, what you can see here, is that changes in this low frequency part are obvious. Something was happening. But the thing is, it didn't happen immediately. Statistically speaking, something happened around 20th hour of operation, and then this error starts to spread, the change starts to spread like this, around 1 Hertz. So we are talking about this interval here. So it started around T20 onwards. A little bit at the same time, something started to happen just above 10 Hertz. So this is 11 Hertz, and I guess it is somewhere around here. And if I remove this part, one can say that there are some changes here. Are they big or not? Compared to the changes here, these are rather small. But the divergence says that these changes are significant. Sorry, let me change the color. But these changes are significant. What this means, I'm not going into the fact what was happening. We can discuss it. But what I'm telling you is, you don't have to look at the ice curves anymore. You can just calculate the difference, the distance between each ice curve, and get a map like this. How much each frequency changed over time. And we can see here that there were no changes at all. Blue, this color map here says deep blue, there is no change. Yellow, there is significant change. So this is how our experiment evolved. Let's go to the second condition. It is a little bit more interesting. So again, the spikes are the places where we did ice curves. There are more than 80 ice curves here. And you can see the ice curves on the bottom left on the slide on the graph B. Again, the red one is the initial and the blue one is the target. And one can say, look, we can simply say that there are changes everywhere. The blue ice curve is simply expanded red one. The changes are everywhere. Well, not significant changes due to variations in our system and everything. The spread of the distributions functions are so big that some of those changes are not statistically significant. And if we draw again the distance map, we can see that statistically significant changes were occurring above 10 Hertz. So this means that this part here are significant up to here. This is not significant. This part here is this part. And although these changes are rather small in absolute values, they are statistically significant. And we can safely say that there is a change in those frequency ranges. Again, I'm not saying what these changes mean for us. I'm just saying that there are statistically significant changes. And our final and most interesting case is the third condition. As you can see, because this is a case of high fuel utilization, even the voltage was not stable that much. There were some fluctuations in the voltage. The spikes, again, are the places where we did ice curves. The changes in the top plots, the fluctuations were mainly caused by our improper control of the steam generator. We were pushing it in a rather strange operating condition. And on the graph B, you can see the ice curves. Again, red one is the reference one, the blue one is the last ice curve. And they're all over each other. One can say, yes, nothing changed. What we were able to find with analysis of the ice curves are these intervals, where there are some changes around 10 to 100 Hertz, and the times correspond to these flicks here. And although these changes are not visible clearly in this region of the ice, we can see that there was some flickering. Something happened, then everything resolved, then again something happened, then it resolved, and again something. Afterwards, we saw that it was a fluctuation of the steam generator, but we were able to see it like this without any painful analysis of the ice curves, visual. These are the benefits, the final benefits of having statistical analysis of ice data. You don't have to look at ice curves if you have a lot of them. And of course, if you are characterizing a single sample or you do a small set of experiments, of course you're going to see the ice curves. I'm not saying you don't ever look at them, but if you have a set of long-term experiments, you would like to see a degradation, you can use such tools for automatic change detection, which are capable of reacting only on statistically significant changes. The benefit is you don't have to train them. You can select one ice curve that by your expert knowledge is a reference one, nominal one, and make relative comparison to that point. You can always change which one is a reference one, the calculation of this is rather fast. So I'm providing all the code, how this works. I'm not going into details, rather slowish today. I'm just going to, the code is there, the documentation is here. I'm not going to bother you with focus on numerical implementation. I'm giving you, if we click, I would like to click here just for you to. Yes. This is what I want to, sorry. This is what I want to show you. All the data from this experiment is available on this link. It is a huge amount of data, more than 3 gigabytes. Coming from Europe, takes some time. I'm not downloading 3 gigabytes of data, by the way. I'm just trying to list the files to show you the files that are listed. You can download them freely, use them whatever you want. While it is downloading, what I provide there is, if I go here, I'm providing time domain data for each ice. So for each ice, there are these DRBS time domain data. There are calculated ice curves that, if you don't want to calculate them by yourselves, they're calculated already, plus all these implementations to recreate all these 3 slides. So when these time domain data are 3.3 gigabytes, download them if you want or not, whatever. The first file is the file that has the results of the blue lines, of the blue plots, and these other files are ice curves at each particular point. In the implementation that I'm providing you, this is everything on the Git repo. It downloads everything by itself. You have the link to the storage again here. You can use the pre-processed data. You can just click. You don't have to screenshot anything. Take care that is 2.5 gigabytes. And here is all the details, how you can do it. And I'm not going into it and generate these plots. So what it means is you can just come here on top of it, and instead of this, put your ice curves, select your reference ice curve, and start from this cell onwards, and you will get such plots for your own experiment. Simple as that. You can recreate it, or you can try it. I'm not going to do it. I tried yesterday in the hotel. The internet shut down. So I'm not going to download 3 gigabytes of data here. That's why I'm going to jump over it. Everything is there. There is no time limitation. It will be there forever with some quotation marks. So, okay. At this point, I had this slide coming on, but because we have drills today, let's go 20 minutes more. Next thing, what I'm going to show you is something that I talked about on the first day, and it was that when you are calculating ice, when you are calculating DRT, I told you that you don't need regularization anymore. So I have to take a sip of water. Sorry. We have. Okay, no problem. I will because this is from the next lecture. I will stop ad hoc wherever 10 minutes. So when it comes 11:15 local time in this room, I will stop. So I told you that we have this neural network approach for calculating DRT, and that we can calculate it like this. So this is now the complete schematics. There is a missing part here, j omega L. I will edit. So this is the encoder decoder that I was telling you yesterday. A place to estimate serial resistance, a place to estimate potential inductivity, calculate the DRT through the neural network, make this integration, and get the real and imaginary part of the ice curve. And this is how the training pipeline goes. I told you that we can plug in here second order derivative regularization. And I also told you that you will not need this ever again. If you do long-term experiment, check it. If you do only single characterization, most probably it's nice. So let's see how this works. I have a DRT plot here from one experiment. It shows, the blue line shows two peaks, and it is one that is smoothed with regularization. And the orange one is exactly the same ice curve, but without any regularization. We can say that there is a cluster of peaks on the same time areas, but it is clear that this time peak, if it's dominant, it's not at the same point here. Which one of those is the proper one, and so on. It is chaotic. We don't want to look at the orange type of curves. We would like to look at the blue types. But what I'm going to discuss now is, as I was showing you with the ice curves, we should not even look at these DRT curves, because we can have a tool that can look at these things for us. So how can we do it? There is one thing, as you saw in the Kolmogorov-Smirnov test, although I was constantly talking about probability distributions, the actual tests work on cumulative distribution. So if you don't have this concept from statistics, a cumulative distribution, usually it's with capital letters of x, is an integral minus x to x. So this is the PDF. This is the cumulative CDF. So the CDF is an integral of the PDF. So what it means is, what if I integrate these functions numerically? I actually do cumulative sum. This is the function, nothing special. And I do the blue one and the orange one. And this is the result. The spikes are gone. Why are the spikes gone? What is the purpose of it? I did nothing special, I just integrated. And there are no spikes anymore. Well, the thing is that imagine what we were talking the first day, that if we have a spike like that, it might be really high. What is the area under this spike? The area under this spike is rather small. So it has no particular influence on the shape of the orange curve. So by just integrating it, we are smoothing it out. These huge spikes are gone. And now we can look at something that can be called cumulative DRT. The name is something that we came up. This is something that we are currently working on. I don't know whether the name will stick or whatever. And now we don't have spikies anymore. We can easily compare these two curves. How can we compare it? We're going to use something called a Wasserstein distance. I'm going to discuss what it is. I have 5 more minutes. And I'm going to, sorry?
But we have about 30 minutes for
30?
Yeah, 30 minutes for because of the drill. 오늘 그 민방 훈련 때문에 지금 11시 반이 아니고 20분 더 해서 11시 50분까지 5시간.
Uh,
Yeah. Yeah, please take your time
just
as
let
you want.
me
Yeah.
know when to stop, so
Yeah.
I don't.
Uh,
Thank you very much.
10 to 12. We have time. 10 to 12.
Yeah. Okay. So, why is this integral actually smoothing out? Why is this integration smoothing out these spikes? Well, it comes from a theorem in Fourier transform. This is where it is visible. I'm not going to put Fourier transforms anymore. Don't worry about it. I'm saying because these spikes are high frequency parts. And if we have a signal that is spiky, let's say we have a spiky signal, and we have another signal that is an integral of that spiky signal. How does this affect the spectrum? Well, a Fourier transform of an integral function is 1 over j omega of the Fourier transform of the original function. What does this mean? I'm going to find a clear spot and draw it here. What does this mean? Well, it means that we take the original function, and let's say the function has some spectrum here, and there are these spikies that are high frequency. And we multiply this spectrum by 1 over j omega. And 1 over j omega is a function like this. Let's take another one. Is a function like this. So what in essence this integration is doing is canceling out high frequency parts and expressing low frequency parts in such a way it does an automatic smoothing. We don't have to do anything. So we smooth it out, but this is not the final solution of it. We can go even further. I will come back to this slide. So we said, does the integration solve everything? Now we smooth the DRTs. We don't need regularization. Is it done? Well, no, actually. This integration makes a little problematic part. All the tests that we were looking at, Kolmogorov-Smirnov, all the divergences and everything, work under the assumption that the function that we're analyzing is a PDF. What a PDF means, it says that the integral of minus infinity to plus infinity of the function must be equal to 1. But for DRT, this is not the case. So this means that all of the above tools are not applicable. But we can normalize it. When we do a normalization, we actually make an additional problem. Imagine that we have 2 DRTs calculated from 2 consecutive I's. And the only thing what happened is that a resistance changed. So this means that the ice curves just blow up. In the DRT sense, it would mean that this peak just blow up, this peak just blow up. It didn't move. It didn't move left and right. It just expanded. And if I normalize these two stuff so that they have integral over 1, I will not distinguish them anymore. They will be exactly the same. And our tools will say there are no changes in the DRT when there are clearly changes here. So we cannot use these tools directly, but luckily for us, there is a shortcut. The shortcut is called an optimal transport. And I'm going to explain now what an optimal transport is. As with everything in statistics, it comes from the military. The question is, the problem is the following. We have several companies that are producing components for making bombs. And there is a central, and so these are the blue dots. And the red dots are factories that are actually producing bombs. We would like to transport the raw materials from the blue dots to the red dots in the most efficient manner, while in the same time we want to transfer everything that is blue to become red without any loss. And this problem is not simple, because we have to take into consideration the cost of moving something from A to B, the timing, and the amount. It might happen that, like in this scenario here, a part of the blue thing can go here and another part can go here, or we can select, should we put everything here or everything here, and stuff like that. So this is a rather complicated optimization problem. How does this affect us? Well, if I go back here, we stop again and start so I can clear it. Our idea, we can exploit this. Sorry. Where is this? So how can we exploit this? Well, our question can be converted into the following. We have this blue area here. What should I do in order for this blue area to be moved around, maybe even to other frequencies, so that I can recreate the orange? So as if, imagine that I have a pile of dirt, and I would like to change the pile of dirt from the blue shape into the orange shape, and I have to take some shovel. Should I just shovel locally, or take a bucket and move somewhere else? But my goal is to make the blue one look like the orange one. But in this case, what we can see is that there is not enough blue sand to make orange. So at some point, we have to start adding orange. And this is where the concept of optimal transport comes into effect. So let's see it. So this is the concept that we would like to use. So we have our reference DRT, and we would like to make it to our target DRT. These are time points. So if I do it like this, this is my DRT. These points here are actually this. So imagine that I take this column here and I try to move it, say that this is the blue one, and I try to move this column to here, this column maybe to here, and so on and so on. So the goal is to transfer everything from the red to the blue ones as a dots, or transfer them as a buckets or whatever. The idea is, what you have to take into account are the following two things. The result is a matrix that shows me how I transported mass from one DRT to recreate the other. There is a case where this is called optimal transport, which means that mass 1 and mass 2 are equal. So I don't have to either add additional sand, or I don't have to destroy any additional sand. But as we saw in our DRT case, this is actually not possible, because our DRTs can expand and contract. So there is additional stuff that is called unbalanced Wasserstein distance. So let's discuss first the balanced case. As I told you, we have mines and we have factories, and we would like to transport raw materials from the mines to the factories. We have to take into consideration the transportation cost and penalty of permutation. This means that it would be easier if the first factory gives it here, the second factory here, so they do not have to distribute on to multiple factories, but this is usually possible. So in mathematical terms, we would like to get some matrices like this here. How red dots are becoming blue ones. That is the mathematical problem of this. So, okay. We have to solve this LC. It's called the loss cost function. And these are some mathematical concepts. I'm not going into it. Our goal is to find this permutation matrix. Which permutation matrix? This means how should I shovel the sand with the minimal cost? That is my question. What in DRT sense, it means what are the minimum things that I should do from my first DRT? Let's draw it. If I have, this is the blue one. This is the yellow, the orange one. And if I have a spike, for example, here, the question is, what are the minimum efforts that I have to do in order to make the blue one a red? So maybe I will take this probability mass and move it here, this here, and I will start adding new mass here. Maybe I have to remove something. If this was going, let's say this was going here, maybe I have to remove this mass and so on and so on. So that is the question. What are my minimum efforts so that I can reshuffle this back and forth? Okay, so in the unbalanced, so this is the balanced case. This means that I can move everything around. There will be nothing lost. There will be nothing missing. But in the DRT case, unbalanced, we can have a case where we either need to destroy something, let's say the DRT decrease, or we have to add something new, the DRT blowed up. And this is the case that we are going to be solving.